Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 2 of the lecture on coincident frequency analysis. This is the 12th lecture in the course on statistical methods in hydrology. In part 2, we're going to talk about the total probability method for coincident frequency problems. Now we're going to continue with the tributary stage problem where we're looking at stage on a tributary, which is dependent on both flow on that tributary and stage on the main stem that might cause backwater onto the tributary and affect the stage. Right? So the information that we have for our analysis, so we have a record of annual peak flows on the tributary as variable A. And remember, variable A was our more influential variable. And so we're going to build our annual peak frequency curve for the variable we care about from the annual peak flows on A. For variable B, we have both daily and annual peak main stem stages. Right, remember, variable B was our less influential variable, and we're going to be looking either at flood peaks or daily values, depending on the coincidence of flood events that are going to drive our variable C. And the information that we want is going to be an annual peak frequency curve for a stage above the confluence, which is our variable C. Right, so for our variable A, we're going to be estimating an annual peak flow frequency curve. And for variable B, based on our daily stages, we're going to look at a daily stage duration curve, right, for the main stem. Now note, this is our case 3, where we're not necessarily assuming that a flood event happens on A and for B at the same time. We're looking at a flood event on A and then stage on any given day for variable B, which is why we're looking at this daily stage duration curve. Now, I had said back in the time series analysis lecture that we can't really estimate probability from daily stages because they're not independent of each other, but that sometimes we do. And in this case, we're going to estimate stage on any given day from the duration curve based on my daily stages, right? So I'm assuming in this case that flood events on A are happening when we don't necessarily have a flood event on B. Now, the daily duration curve is being showed as percent of time exceeded. And note, while my exceedance probability axis on A has 0 on the right and 1 on the left, I'm drawing my duration curve with 0 on the left and 1 on the right. This is how we generally draw duration curves. So the way I'm going to use this information for A and B is I'm going to discretize both distributions, but in different ways. Right? For variable A, I'm just going to pull values off my frequency curve, right? So values of A with different exceedance probabilities, and I'm going to keep those probabilities as exceedance probabilities or cumulative probabilities. Right. Now for variable B, I'm going to discretize it differently. So I'm going to divide up my duration curve into probability ranges. And for each probability range, I'm going to define an index value. And that index value will then be associated with the probability for that range, right? So the probability of B2 is going to be 20%, and B2 will have the index value shown here. Right? Then finally, we have a response function, right? So for each of our discretized values of A, and for each of our index values for B, we're going to do our hydraulic modeling and evaluate the stage at C for each of these combinations. So the way this notation works is that for the 5% exceedance flow at A, and for main stem stage with index value B6, I'm calling it the 5% tributary stage given the main stem stage is B6, right? So B6 here is my condition. So here is my probability of C conditioned on a particular outcome for B. Now, once I've created this response surface, each row of this table is a conditional exceedance probability for C, right? Conditioned on this particular value for B. So this is actually step 1 of our conditional frequency analysis. We have our values from our probability distribution of A. Each are combined with all of our index values for variable B. All of my variable A values with a particular index value of B is going to give me a frequency curve for C that is conditioned on B. So after computing that whole matrix, we get a family of conditional frequency curves for C conditioned on B. One curve for C given B for each value of B. Right, so note that our response at C is just adopting the probability of my value A, but conditioned on the outcome at B. So now I have a family of conditional frequency curves for C given B. So now what? What are we going to do with this family of conditional frequency curves for C? I don't want conditional frequency curves. I want a marginal distribution for C, right? So the way we're going to approach this is to use the law of total probability. Okay, again, you saw this in the multivariate lecture. For me, this is something that you need to hit more than once, and so I'm going to talk about the law of total probability again. Here we have the probability of C, which is equal to the sum across all defined values of B of the probability of C given B times the probability of B. So now we already have conditional probabilities of C given B, and the probabilities of B were just values from our chopped up duration curve. Right? Now, for me, this equation doesn't make a whole lot of sense, and I'm going to describe it in two ways. Having described it both ways in class in the past and then asked people which explanation was more understandable for them, I kind of get a 50-50 split, and so I'm going to show it both ways. And if you want, you can let me know which way worked better for you. Right, so the law of total probability, we can do it with Venn diagrams. So here we have the universe divided up into different possible values of B. And we've divided B into values that are mutually exclusive, meaning there's no overlap, and exhaustive, right? So this is where we divided our duration curve up into probability ranges, right? Then we have an event C that can happen with any of those values of B. Now, since we want to estimate the probability of C, it's going to be the sum of these 5 different intersections, right, with each of the values of B. And each intersection is defined as C intersect B, where the intersection operator is this upside down N. And this is also an AND condition. So each of these areas is where C and B1, for example, have occurred. Right, we have already our conditional probabilities of C given B, right? We have that family of conditional frequency curves for C given B, right? So this is known. We also have a relationship for C given B1, right? That's already seen, right? So now saying given B1 means that our condition B1 is true. And if our condition B1 is true, we've actually reduced the universe as described by our Venn diagram, down to just B1 has occurred, right? So that's changed our probability situation. So this is where this relationship C given B1 is equal to the intersection of C and B1 divided by B1. We're interested in this part of the probability of C, which is therefore a ratio of this area and B1, so the intersection divided by B1. We can rearrange this formula and isolate the C intersection B is equal to C given B1 times B1. And that's one of my pieces of C. And then to estimate the entire event C, then I have to come back and sum up all of these intersections of C and each of the B's, right? So C is going to be equal to the summation of all of my B and C intersections. Okay, so that's showing total probability with Venn diagrams. And some of you might prefer that, and some of you might prefer a more verbal example, right? So I'm going to give an example with weather. And I'm not a meteorologist. I don't know anything about weather. So this might be nonsensical, but just bear with me. I'm going to say if a cold front arrives, there's a 70% chance of rain. And if not, if the cold front doesn't arrive, then there's only a 10% chance of rain. Okay, so what's the chance of rain? Now, I want to know whether or not to take my umbrella. And I only take my umbrella if there's maybe a 1 in 3 chance of rain, right? So what do I need to know here? I've got some conditional probabilities, right? I've got that the chance of rain is 70 if a cold front arrives, and the chance of rain is only 10 if not. So what I need to know is the probability of my condition, right? So this depends on the chance of the cold front arriving. I need to know the probability of my condition. Right, so if there's a 20% chance that the cold front will arrive, right, then I have enough information to solve the problem with the law of total probability. Right, I can take my 2 conditional probabilities and the probability of my condition. Right, so the probability of rain is then going to be the 70% chance of rain if the cold front arrives times the 20% chance of the cold front arriving. plus the 10% chance of rain if the cold front doesn't arrive, times the 80% chance that the cold front doesn't arrive, and that equals 22%, right? So given this, I'm not going to bring my umbrella because 22% is less than 1 in 3, right? So maybe that description of the log total probability works better for you. And go ahead and let me know whether you like the Venn diagram explanation or the chance of rain explanation. So we have our family of conditional probability distributions of variable C given variable B, meaning tributary stage given main stem stage. And now we need our conditions for our variable main stem stage, right? So how did we do that? Well, we took that daily duration curve of main stem stages and we divided it up into probability ranges. So this is creating ranges that are mutually exclusive and exhaustive. And for each range, I'm going to specify an index value for that stage, and that index value is going to assume the probability of the range, right? And remember, these are incremental probabilities, not exceedance probabilities, but our variable A was described with exceedance probabilities, okay? So now we can go to step 2 of our analysis. Right, step 1 was developing these conditional distributions of C given B based on our response surface, and our values of C all adopted the exceedance probability of A, but got conditioned on the value of B. Right, now I'm going to say for any given level of variable C, and I'm drawing a level of C on the diagram here, I'm going to come across all of my conditional frequency curves and see where they intersect this one value of C, right? And I'm going to compute those exceedance probabilities. Okay. Then to use my law of total probability, for each of these points, I'm going to say I want that probability of C given B1, which I've computed by coming down from the curve at each point, times the probability of B1, which was just the segment of the duration curve, right? So if I do that for this value of C, I add up all of these products and I get 0.56. So the exceedance probability of C1 is equal to 0.56. And if I do that for variable C at every level of C going across the curves, then I can trace out the marginal frequency curve for variable C. So this was combining my 2 probability distributions and my response with the total probability method. And I've ended up with the probability distribution of stage on the tributary based on flow on the tributary and stage on the main stem. Right? Now, what about case 4? Right? We just did case 3 where we said events don't necessarily happen at the same time. So when there's an event on A, it's just any given day on the main stem stage. But what if events do happen at the same time, right? So maybe we're having an event on stage B at the same time as we're having an event for flow A, right? In that case, we're going to replace the duration curve for B with a frequency curve, right? It might be an annual maximum frequency curve, right? If we are seeing the annual maximum on B at the same time as the annual max on A, right? Or it might be based on a sample of what are called coincident events. So in this case, we take our annual maximum tributary flows, and at the time of each of those annual maximums, we look up what is the stage on the main stem at the time the peak was occurring on the tributary, right? And we pull those values for B and use those as a sample for estimating an annual frequency curve, right? So instead of an annual maximum frequency curve, it's called a coincident event frequency curve. Okay, so for case 4, we're going to use that frequency curve, one or the other of those frequency curves, in place of the duration curve, right? We're going to discretize the frequency curve for B in the same way that we discretized the duration curve, right? So now our inputs are going to be our flow frequency curve for A, the tributary flow, and it's going to be a flow frequency curve for B, but that we're using in the same way that we use the daily duration curve. So the difference is going to be in the magnitude of the probabilities. So for any given main stem stage, right? So let's say we're coming across horizontally. For a given main stem stage, the probability of seeing that stage on any given day is going to be quite a bit lower than the probability of seeing that stage as the largest value of the year as an annual maximum, right? So the annual peak frequency curve for B is going to be quite a bit higher than just a daily duration curve for B. Right, so that's the difference we're going to see is much higher probabilities now for a given level of B. Now, note though that the frequency curve for B might be annual extremes or it might be those coincident events, but either way, it's going to be higher than just any given day. Right? And for discretizing both variables, we discretized variable A, the tributary flow, by just pulling off values with a given exceedance probability. And we're going to discretize now a frequency curve of variable B in the same way that we did the duration curve, by dividing up into probability ranges, and for each range choosing an index value for variable B, my main stem stage, and assigning it the incremental probability of that flow range. From that point, the analysis works in the same way that we just walked through. Now we get to case 5, right? The flows at A and the stages at B are not perfectly correlated, but we also can't assume that they're independent. So if I'm plotting my tributary flow versus my main stem stage and look at the point scatter, we don't have a big round scatter of points that might show independence. They're kind of starting to gather around a straight line showing a linear relationship between the two. So I'm looking at maybe too much correlation to assume independence. Right? So we've got some correlation between A and B, and it's too strong to ignore. Right? So if we have some correlation, where before we were able to use a marginal distribution for probability A, meaning just a frequency curve for only variable A, the tributary flow, we would instead need, in this case, some joint distribution of A and B. If they're correlated, we need to define a joint distribution. Or from a joint distribution, we can also define a conditional distribution, right? So the way I'm going to show it is as a family of conditional probability curves for A, right? Each conditioned on some value of B. Now, this is very hard to develop. We need maybe an order of magnitude more data to develop this joint distribution for A and B than we did for just developing a distribution for A and for B separately. So it's unlikely that we will have a conditional distribution family like this, but I'm going to show how the total probability method works with this input before going on to another method of doing this evaluation. So if we have this family of conditional distributions for A given B, that will be our first input. And then our second input is still going to be that distribution for B alone that we've discretized by dividing up into mutually exclusive and exhaustive probability ranges and assigning index values. So step 1 is going to be slightly different, only in that when we're making our response surface for tributary stage C, given tributary flow A and main stem stage B, instead of just using a single set of values for A, each with a given exceedance probability, to pair with each of our values for B, instead we're going to have to pull values off of each of these frequency curves for A, right, to pair with a given stage for B to get each of these conditional frequency curves for C. Right, so we don't have any more model computations to make our response surface, but they're not based on all the same values for A crossed with the same values for B, right? It's different values for A in each case. But after that slight difference in step A, step 2 is exactly the same. So the conditional curves for C given B, or tributary stage given main stem stage, those curves are going to be a little bit further apart in this case, but we're going to do the same total probability method to combine these conditional curves into one marginal curve for C. Now, the outcome that we're going to see, though, is that the frequency curve for C is going to have a greater variance or standard deviation. Now, this isn't surprising, right? The situation we're modeling here is that there's some correlation between the tributary flow and the main stem stage. So tributary flow and main stem stage tend to be high at the same time. So if they tend to be high at the same time, then a higher tributary stage is more likely, right? So the upper end of our frequency curve would be expected to be higher, right? And tributary flow and main stem stage tend to be low at the same time, so the lower end of our frequency curve is going to be lower. So when we incorporate correlation, we see that we have a higher upper end of the frequency curve. And that fact should inform our decision of whether or not to assume independence or acknowledge the correlation between our variables, right? Because if we don't acknowledge the correlation, then we might be underestimating the frequency curve. Right. Now, this analysis The total probability theorem method is available in SSP, and we're going to be using SSP to do case 3 in the workshop, and so I'm going to run through what the SSP interface looks like. Okay, so coincident frequency analysis in SSP, again, using the tributary stage example, and I thank Mike Bartles for these slides. So we have our variable B. SSP is going to assume that this is case 3 and that this is a duration curve. So variable B is a duration curve, and we can either import from a duration analysis that we did in SSP, or we can define our duration curve manually. Once we've got a duration curve, there are different ways that we can divide up the probability range, right? We can define from index values where we supply the index values, and SSP will go in and divide up probability ranges around the index values. Or we can specify probability ranges, and SSP will go into each probability range and pull out an index value for us that summarizes that range. Or it can be done automatically. Now note that the probability ranges shown here are a lot more sensible than the ones I showed on the previous slides. We're seeing that where the curve is really flat, the probability range is wide, because we might as well show this whole range with the same index value that's not going to differ much from any value in the range. But where the curve gets really steep, we want narrower and narrower probability ranges, right? So the index value is more representative of all the stages within the range. Okay, so this is the specification for variable B. So variable A, remember we can either be assuming that A or B are independent or not independent. If A and B are independent, then we just need a marginal frequency curve for A, and we can either use an import from a frequency curve we've estimated within SSP, or we can enter it manually. And if we're choosing that A and B are not independent, then we need to do a manual entry of conditional distributions for A given B, conditional distributions for our tributary flow given our main stem stage, right? And here's a plot of perhaps some conditional frequency curves. Again, it's unusual that we are able to develop these frequency curves. Right. Next tab is the response surface. Now note that this is turned sideways from the slides I showed earlier. So now we have values of A going down the first column and values of variable B going across, right? And if we've got our response surface as just a matrix between each value of A evaluated at each value of B, it's going to look like this. But if we have our modeling done that each index value of B has different index values of A, then we're choosing the second radio button. And what we'll have then is for each index value B, we're going to have a column of A versus a column of C, column of A versus a column of C, right? But the simpler case is A's in the first column and B's going across. And each value in the table is the response at C. So this is our tributary stage given these tributary flows and these main stem flows. Hopefully this curve is visible. When you hit compute, we have the computed marginal probability distribution of tributary stage C given my inputs for A and B and my response surface. Now, it's not shown on this slide, but there's also a button where you can plot your conditional probability distributions for C given B, and then see the computed marginal distribution of C on top of it. As I mentioned, often the assumption of independence really isn't valid, meaning the correlation is a bit too high to ignore. So we want a joint distribution between A and B from which we can compute conditional distribution of A given B. But as I mentioned, it requires at least an order of magnitude more data, and it's very difficult to develop this joint distribution, right? So there's some other options. One option is to do continuous simulation, right? If we have a time series of both A and B covering the same time period, then we can do simulation to get a time series of C, right? And from that time series of C, we can pull out our annual maximums and do a frequency analysis of C, right? So it's just like having observations of C, except we're doing our analysis on modeled results. Right? Another option is to estimate marginal distributions for both A and B and estimate a correlation between them, and then do correlated random sampling in a Monte Carlo simulation, right? So that's going to be what we look at in part 3 of this video. So this is the end of video 2 of coincident frequency analysis, and we'll move on to part 3.